Hello viewers, this is Ilkka Kokkarinen speaking, and I'm here starting a new YouTube lecture series, topics on introductory data structures and algorithms. So I used to be teaching data structure course in the Ryerson University Chang School of Continuing Education for a long time, and before that back in Finland for 5 years in Tampere University of Technology, as it was called at the time. So these days Ryerson is called Toronto Metropolitan University, but tomato. So just to get an inspiration, just so that I can create new YouTube videos. And this video series that I'm starting now, so this is intended for students taking the first course on data structures and algorithms, like the pretty standard outline looking at any university in North America or Europe. So then in this video series, I'm gonna be looking at the topics that I maybe are not covered enough in this kind of introductory course, which topics are important and interesting and hopefully fun. So hopefully this is gonna be an enjoyable series for such students. And today I have a first topic on how to make a linked list the most convenient way. So that's a bit of a different than is taught in the most courses that I have seen. And then I have a couple of other interesting topics in mind, which I'm gonna be recording over the coming weeks. So let's get started with this first topic. We'll look at some slides first, and then this video series, I'm gonna have a GitHub repository, so we're gonna be looking at an example of the way to most convenient way to implement the linked list data structure. So this kind of typical intro data structure algorithm course, linked list and their algorithms are covered somewhere along the in the first 3 or 4 weeks. So depending on whether you cover the big O notation and the array-based data structures before or after. But so let's take a look at some of this linked list terminology. So this now assuming that you've taken that the lecture where discussing the linked list data structure. So now I noticed that a lot of courses and material, they get this terminology a bit of wronger. So let's be careful on the terminology. There's a whole bunch of variations. So what the linked list, so the first big difference that is taught, so is your linked list, is it singly linked or is it doubly linked? So when you have those node objects that can be anywhere in the memory, unlike the elements in the array that are always in consecutive memory locations, and this way allow the random access jumping indexing of the array back and forth. So in a linked list, so your nodes can be anywhere in the memory, and each node has a pointer or a reference. So reference is just a pointer that doesn't allow pointer arithmetic, otherwise so it is a pointer. So low-level languages like C and C++, they allow you to treat the pointer as if it were an integer and then do integer arithmetic. And then when your pointer is pointing somewhere in the memory, so just with the integer arithmetic, you can access like the memory around it. Whereas in Java and Python, so pointers are references, they are still pointers, but the language doesn't allow you to treat a reference as an integer, so you cannot do integer arithmetically. So when you have a reference, the language's type system always ensures that the reference is pointing to a proper object, or it could have the value null. That's gonna be today's big topic, to say that the pointer in a controlled fashion is not actually pointing anywhere. So now, depending on whether you want to allow the traversal of the list only to the forward direction, or do you want to allow the traversal to both the forward and backward. So we have this first distinction. So the list can be singly linked, so every node has the next pointer, versus doubly linked. So every node then has 2 pointers, canonically called next and prev. And then from a given node, you can step forward or backward as you please. Now, this terminological confusion, like I've noticed some material uses the term linear list when they mean singly linked list, but so that is now totally different than independent thing. So independent of whether your list is a singly linked or doubly linked, so it can be either linear versus cyclic. So what does that mean? So in a linear list, so when you have the last node hanging in the chain, so there's no node after it. So in a linear list, so then this next pointer is gonna be null. And if you have a doubly linked list, so then your first node that doesn't have a predecessor, so then the prev pointer is gonna be null. Whereas a cyclic list, so this seems kind of weird in the beginning, but this is actually gonna be a lot more clever idea than it might initially look like. So like the Kekule benzene molecule in the dream, that instead of having the endpoints of the linked list, just the pointers pointing nowhere, that we can turn the list into a cycle by putting the endpoints together like an Naoki's in here. And then the last node, when you follow the next pointer, you get back to the first one. And then if you have a doubly linked list, so when you're in the first node and follow the prev pointer, you get to the last one. So this idea that you have nodes in a circle, so you never have any null pointers in your list. So then independently of that one, so then the next possible distinction, so whether you have the concept of the entire list as a separate concept as opposed to the concept of having a node in the list. So typically how it's done in the textbooks and such, that you have a data type list, and then in the list there is a head pointer pointing to the first node object that is the head of the list, and then the next pointer from there you can follow, so you can get to the rest. And then the list there might be a tail pointer, and then you got the exercises like if you do a stack or a queue, so like which end you're gonna add in constant time and which end so it is the best. But so that's a topic for the stacks and the queues. But then, so we could also have that we don't have a separate concept of a list at all. We just have the concept of a node, and then so the node object at the same time, kind of like the composite pattern in the design patterns when you kids get to that course, that the first node of the chain, so at the same time it's a node, but then it also represents the entire chain that is hanging from it. So the same thing, so it's either a node or an entire list, depending on how you choose to treat that. So that third distinction, whether you have a separate list data type or whether the first node object in the chain, you only have node objects, but the first node object represents the entire list that is hanging from it. So that's again independent of your design choices for the first two items. And then, so if you have a separate list object, and then also like, of course, you need to have some kind of access to the first node. So then this is the big topic of this video. So this is one of those things that seems like it's wasteful, but it's like a false economy thing, that we waste a couple of bytes extra memory and then everything becomes like a way easier. So all the material that you see on list, they always basically say that you have a head pointer pointing to the first node, or that is that the rest of the nodes are then hanging following the next pointers. But then an alternative is that you don't have a head pointer, but you have an entire some kind of a head node that is acting as the header. So because the nodes have a next pointer, so then you just have this kind of unused header node. And then, so if you have to have the header node object, that just follow the next pointer to get to the actual first. So now, of course, the inquiring viewers are saying that that's just silly, like you just need one pointer, the head pointer pointing to the first node. So why would you have like a totally unused node that has like an unused payload field, and you're just wasting memory? So, but that's today's topic, that especially if we do a doubly linked list and if we make it cyclic, so the header node turns out to be like a way better way. I'll explain the theory first on the slides, and then we look at some code. So then you see how much better all the list methods become when we use a header node instead of the head pointer. So this gives us like a 2 to the power of 4. All of these are independent. You can make the design decision. So 16 possible combinations, but I argue that only 2 are relevant. So if you wanna be saving memory, let's say you're like doing the hash table, like you're gonna be doing after the middle of the data structures intro course, you have like a whole bunch of the linked lists hanging from some kind of array, and then you first use a hash function for the data object to decide which of these linked lists hanging you're gonna be using, and then once you've done that, so then everything is just a singly linked list operation. So when you have the hash table with the collision resolution with chaining, then they just become singly linked list operations. Now we want to be saving memory. So we have an array of head pointers, and each head pointer is pointing to the linked list that contains the elements of the hash table whose keys they hash into that particular slot in the hash table array. But that's a topic for a different video. So that's the head pointer singly linked linear, and then the first node object represents the entire list. So that's when we are being stingy on memory. But then, so now in this video, I'm gonna argue that like if you do a doubly linked list, like always make it cyclic and always make it the header node. So I'll explain the reasoning in a couple of slides, and then we look at some example code. So the problem with the linked list and all of these data structures so is this existence of the null pointer. So the famous computer scientist Tony Hoare, who's known for a bunch of things from the 60s, like a quicksort and then a whole bunch of parallel and such language formal verification stuff. So he's famously called the null pointers his $1 billion mistake, and it's been a couple of decades now since he said that. So how many zeros do we need to add to the end of it? So God only knows. So these days, if you look at the languages that have come out over the past decade or so. So the big thing in those languages is the compile time detection of null pointer errors, because so null pointer errors are so incredibly common and incredibly annoying that we need some kind of language support to get rid of them. So now if your pointers and references can be null, so this is just a universal thing, like independent of the data structure that you're doing. So now every time you're doing pointer dereferencing, I've noticed over the years that the students like they tend to err to the side of caution. Of course, it's better to err to the side of caution rather than to err to the side of destruction. So a lot of people are like extra careful about the null pointers. Like for example, I've seen a lot of code where somebody's testing whether a pointer q equals so it's not null. So then they assign it to pointer p, else say p equals null. But it is not the assignment and comparison that is dangerous with the null pointer. So that doesn't crash anything, even if you assign a null value to a pointer, or whether you compare a null pointer value to anything. But it is the dereferencing. So if you try to actually follow the pointer to the memory address that is pointing to, so the whole point of the null pointer is that the null value tells the computer hardware that it's not the real memory address. So then any attempt to dereference a null pointer address so causes a hardware trap, and your program crashes on the spot. And then if you're a low-level guy, so you get the program, the illegal operation, like in the old-timey Windows, you get the dialog program as executed on illegal operation and will be shut down. So not the greatest designed error message. I remember a lot of people in the 90s got scared that they done something. What does the word illegal mean to an average person. Think about that for a moment. But so this idea that the null pointers, they seem like so useful, but that now you're constantly writing code. Like imagine, so you're writing that method to remove the given key from the singly linked list. So first test the special case if head pointer equals null, do nothing and return. And then you can handle the special case of removing the first node in the list. That if it's the first node that contains the key that you want to remove, so now you have to modify the head pointer, make the head pointer point to the successor of the first node. And then a lot of students are extra careful that they even handle that if the next one is null. But so that's the being overkill careful. And then otherwise you traverse through the list looking for the node whose successor is the one that contains the key that you want to remove. And then you modify the next pointer of the predecessor node to make it point to the successor of the node that you want to remove. So needlessly complicated, so because of the fact that now we have edge cases and special cases. But now in the theory of design patterns, so there in the Gang of Four books, so there is the null object pattern. So of course would be better if we have like a language compile time verification for the nullness. But so this idea is that if you can have like a null pointers when you have some kind of a node objects that are all like the same type, so just allocate an object that you're not gonna be using actually to store any kind of payload data. You call that something like a null, like a my null or something. And then so in your code, like whenever you would assign a pointer to that type of an object to be null, you actually assign it to the point to the null object instead. So you never have like a real null pointer with the lowercase n, but you always so when your pointer is pointing to that special object, so then it is you behave as if it were null. Now, what is the advantage? So the advantage is that unlike the null pointer value, the actual lowercase null or nil or whatever it's called in your favorite language, so that the dereferencing this kind of pointer doesn't hurt you. So then you don't need to be testing whether your pointer is null before you dereference it. So now your code, you can eliminate all those tests whether the pointer is null. So when we look at the doubly linked list cyclic header node implementation after these slides, then you'll see that everything becomes like a way simpler once we do this way. So now, so this is now, okay, here would have been the slide that I just explained. So the fact that you have a separate head pointer, so now you have to handle in the linked list algorithms dealing with the first node, you have to handle it as a special case. And then, so especially removing the node with the given key. So now you have a three-way. So the first handle the special case of not doing anything if your list is empty. Then the special case of removing the first node, and then the general case of removing the later node. So this is too many cases for my liking. So I would only like to have one case. How can we be like a totally uniform? Yes, we can. So now my instruction for this first video, so I don't even think about it, just do it. Like if you have a doubly linked list, so if you choose to do it that way, so then don't think, just do it. You get all the benefits and this can never ever hurt you. Is that your doubly linked list, first of all, should be cyclic, so that you don't get those annoying null pointers in the beginning and the end, even if you use the null object. And then instead of having a head pointer in your list object, head pointer pointing to the first node in the cycle, that you have a header node, and the header node itself is part of the cycle. So then this header node, so its next pointer points to the first element, the first node in the chain, and then the prev pointer points to the last node in the chain. But this header node itself, it's not part of the payload data. So even if it's a node and it has whatever you call it, key or data, the actual data that the node is storing, that the header node of course has that field because it's a node the same as all the other nodes in the chain. But then the value of this header node key field, so it's never used for anything. So now notice that if the entire list so has n keys stored in n nodes, so then this cycle actually always has one more, so n plus one, because the header node so is always part of this cycle, and so it just carries no data, but this cycle is unbroken. So we're not gonna get any special cases dealing with the first node or dealing with the last node the way that we would have if we have like a separate head pointer pointing to the first node, because now we can update the head pointer if we are removing the first node, whereas if you're removing some other node, then you can update the predecessor and successor neighbors. So that's two cases. I only want to have one case. So now this header node, once you have access to it in the list object, so then you can follow the next and the prev pointers to get to the first and the last node in the cycle. Now, okay, obvious question, we create the linked list, what if it's empty to begin with? No problem. So then this header node, so it's next pointer and it's a tail pointer that normally point to like whoever's the next and the previous guy in the chain. So then it's this header node is just giving itself this kind of a self hug for a comfort. So the header node, the next pointer points to itself, and the prev pointer points to itself. So then you can have an empty list. So then when you start traversing the list, so then you immediately end up back to the header node, and that's how you know that your traversal is done. And then the singleton list, so when there is a header node and one node, so then that one node is both the successor and the predecessor of the header node, and then the header node is both the successor and the predecessor of that singleton node. So there is no special cases. The empty list, the singleton list, the two element list, all of these are handled exactly the same with the exact same logic. Our list methods, as you see, they're not going to have any special cases. Everything is handled the exact same way. So what is advantage that when your doubly linked list is cyclic, and then it's accessed with the header node, not with the head pointer, but the header node. So there is never any edge case situations in any of these methods. So especially there are never ever any null pointers. And then if we think of the header node as the null object for the list, so then of course there is that, but the null object, because it's a node object just like any other object, so then all these list operations, so they don't need any special cases for dealing with the first element or dealing with the last element. So basically all your linked list algorithms become like a massively simpler. So this is like so obvious to me that if you're not about to save memory by doing that other reasonable linked list implementation, so like just automatically do your list this way. So you never regret it. There's no possible situation where this could come bite you in the butt. So the header node itself, so it's always part of the list, but of course, so we write the logic so that we never actually remove that. Okay, so let's look at some code. So I started the new GitHub repository topics in data structures where I'm gonna be putting the examples for this video series. And now my first examples that I just uploaded. So we have two data types, DL list, so doubly linked list. So this is gonna be the entire list as a concept. And then we start by looking at the DL node. So this is the data type that defines the class whose objects are the individual nodes in the memory. So now, of course, in Java we can make this. Why not make it bigger? So let's make this a generic. So the element type that is stored. So now the user code can decide it. So generics are fun and useful. So why not do that? And then So we make all the data fields should always be private. So now in my courses, as I always say, so all the data fields should always be private. So if you want to allow the access, so then provide a public accessor or a mutator method for the data field if you want it. So then private data field, the actual payload data. And then so each node so has two references, next and prev, pointing to another DL node with the same element type. So reading through, so first we have this default constructor. Notice that in the Java syntax, so the constructor doesn't have the generic type parameter there anywhere. So then the key node is, well, the key node when this node is allocated from the key field, when the node is allocated from the heap memory, so Java guarantees that it's set to null. So we don't have a key in here. Then we have the then we have a constructor to set the previous and the next pointer, and then so we have a constructor that okay, now I realize so I should gonna fix that then of course should be setting also the prev and the next to be pointing to this, but just showcases that I didn't have enough test cases, but just bear with me. And then another constructor to create the DL node, so with the given key, so when we know what the predecessor and the successor of the new node are going to be, so then when we construct the node, so we can initialize these fields. And the key field was defined to be private, so we defined two public, so we provide the public accessor, so the method get key, so returns the key in here, and then the set key that assigns a new value into the key field. And then we provide the accessors for the previous and the next. So we don't provide a public mutator, but some of the methods that we try to put as much logic into the DL node. So for example, linking and unlinking, we're gonna make them the node operations instead of the list operations. So if these methods are in the same class, then they can access the private members of another object of the same type. So in Java, the public private distinction is enforced at the compile time, so it's not a runtime distinction. So the private members can be accessed in the methods of the same class. So even if those members are in a separate object, so it doesn't make any difference at the runtime because the access is determined at the compile time. Then we provide the toString method that we're gonna be, so just for debugging purposes. And then, so we're gonna make these doubly linked list operations to be operations of the node data type. So then the actual list methods end up being simpler. So first, the method unlink, so that takes the node out of the chain. So if the node is there in the chain, like it's like a bunch of guys in a circle holding each other's hands. So if I'm here and then there is a Joe is on this side and Mo is on that side, so how do I take myself out of the chain? So I just tell, hey Joe, meet Mo, and hey Mo, meet Joe. So I'm gonna say that the successor of my current predecessor, Mo, so it's then gonna be what they used to be my successor. And then I'm gonna tell my successor that your predecessor is now gonna be who is my predecessor, so Joe meet Mo. So then to unlink the node from the chain, so I just tell my neighbors that they are now each other's neighbors, so I'm out of here. A lot of people in here would feel the temptation, for example, maybe to help garbage collection or something like that, that they would make the next and the prev in this node to be just to point to itself. But then if we don't do that, so then in the technique, for example, dancing links in backtracking. So then we can restore, if the node that we take out of the chain remembers who used to be the neighbors, so then we can link it easily back with the two assignments. So well, question of taste really, but then the next operation, so for the node this, so then given the node, so make that to be your new successor. So then we tell the new successor that its predecessor is going to be this node, and then the new successor's successor is what used to be the successor of this node. So the new successor comes in between the two of us. So what used to be my successor becomes the new node's successor. And then I assign, so my new successor is going to be the new successor. And then my old successor, predecessor, is also going to be the new successor. Remember, the assignments are done right to left, so then this works out correctly. Now, when you write the methods where you don't have like a meaningful result to return, that you have a return type void, so it never hurts you that you return the object for which. So here we return the new successor. We don't return this one. Well, so depends. So I don't know actually which one is better. Should I be returning this or the successor? But like you might as well return something, because doing this so allows these method calls to be chained. As opposed to if a method just return nothing, they just mutate data. So then you can write them as a separate statements. But so if a method returns an object, so now you can chain the method calls and this way make your code more streamlined. So this link successor takes an existing node and makes it to be the new successor of the current node. And then the variation insert successor. So if you're just given the key, so then we create a new node with that key and link that one to be our new successor. So this insert successor, when we have a link successor, we don't need to duplicate the logic. And then, so this everything is symmetric in a doubly linked list. So if you have a link successor and insert successor, so then link predecessor and insert predecessor are exactly the same. Notice the unlink method is just one method, so we don't have an unlink successor, we don't have an unlink predecessor, so we just unlink the node that you want to remove. Now the one thing to notice in here, so because we have a cyclic doubly linked list, so then notice none of these methods has any kind of special edge cases, like for example, what if you want to unlink the first node in the list or the last node? So when they are all in a cycle that is perfectly symmetric, so header node is in there, but now it's your responsibility never to unlink the header node, because then, well, I guess if you just want to make the entire list empty, just unlink the header node and let the garbage collection take care of the cycle that is created. So, but normally we wouldn't be unlinking the header node, but then any other node, doesn't matter whether it's a first node, last node, whichever node, the logic is exactly the same and it's completely unconditional. So we have the concept of the doubly linked list node in here, and the nodes can link and unlink themselves to each other. So now that we have this capability, so let's look at the concept of an entire doubly linked list, so cyclic and header node. So again, so we have this concept of the element type, so we define it as a generic class. And then, so each this DL list object so has a header node. So because so this header node is never gonna change, we make it final. So then I've named it in all uppercase. So it's like basically it's a constant per object. It's not really a named constant, but like each of the, when you have a multiple DL list objects, so then each one has its own header node. So then this is like a final constant per list object. So I stand by my naming. So then this creates a node that points to to each other. So initially this cyclic list is empty. So you recognize an empty list from the fact that this header node is its own predecessor and its own successor. So now define a couple of useful constructors. So because the header node is initialized here in the initializer, so we don't need to initialize it in the constructor. Now as a Java sidebar, so the Java material often teaches you that when you create an object, the first thing that happens is that the constructor is executed. But actually, so if you have a field initializers like there in the line 13, so the field initializers are guaranteed to be executed before the chosen constructor executes. So just for convenience, so often we want to create a list from a given known array or list of elements. So we make a constructor, so given an array of the keys that you want the list to contain, so a loop through the keys. So if we want the first key in the array to end up the first in the chain, so notice when I loop through the keys from beginning to end, so then I have to add each key to become the predecessor of the head. So each one I always add to the end of the list. But from the header node, so inserting the successor and inserting the predecessor, it's all the same, just the symmetric. So both are constant and big O1 operations. And then the same idea, so that for an arbitrary list of keys, so notice the Java, the for each loop works not just for arrays, but works for any kind of iterable, so including the Java collection. So loop through the keys and insert each one to be a predecessor. So now the linked list operations, let's take a look at them. So first the logic of inserting to the front. So notice that it is a one-liner. So just we insert a new successor to the header node. No special case. So well, here we wouldn't have special cases anyway, but notice all the work is done in the DL node, the node class. So it is just one line. And then the insert back is symmetric. So insert predecessor, new node with the given key. Now the removal. Now we still want this to give an error. So otherwise, well, if we have an empty list and then we unlink it, so basically this would still work, but we still want this to inform the user that. So how do we recognize that this kind of a cyclic header node list is empty? We recognize it from the fact that the head is its own successor. Notice that because the next is a private field in the DL node class, so now we have to use the get next accessor method. I'm pretty sure that the modern compilers and virtual machines optimize this kind of access anyway. If I'm wrong, so Java people can correct me. So to remove the first node, so there we get the successor of the first node, and then tell that node just to unlink itself, and then this returns the node that was removed. Remove back the same, but then we just unlink the predecessor node of the head. To string, so what this is gonna be segueing to the topic of the video that I was planning to do as the second video, so accidentally quadratic or don't be a Schlemiel, so that we don't write the ON squared algorithm when we could have written an ON algorithm. So what is, as is taught in the Java courses, that when you build up a long string from small pieces, so then because Java strings are immutable, so otherwise I always doubt the advantages of immutability, like if you can make your data type to be immutable, just do it, don't even think. It's got a zillion benefits, but then there is also one downside. That's why we don't be like a bearded functional programming weirdos and make all the data types to be immutable. So then if you repeatedly concatenate the immutable strings, so because the concatenation has to create an entire new string object. So imagine that you have a 1,000 character string, and then you concatenate 2 more characters to the end. So this triggers the creation of a new 1,002 element string object, linear copy of the 1,000 characters to the new string, and then the 2 characters. So this, if we build up a long string this way, so we get an O(n) squared operation, whereas the string builder in Java so behaves the same as an array list. So in the say this is another good thing to know, just in case that you didn't know. So how this works, both the string builder and array list, is that they internally use an array, but there is some slack space in the end. Like for example, that if you have a 1,000 element array list, so then the size might be like a 1,600 or a 2,000 or something. So that the underlying array that contains the data is actually larger than it needs to be. So we are trading space for time. So we got so much memory and we got so little time that they will happily always do this trade-off. So as long as there is slack space available in the end, so now mutating, so adding stuff to the end, so it's a constant time operation. Now, eventually, when you keep adding and adding, eventually you run out of the slack space, at which point then allocate the new array, typically twice the size. Now we're going to have to copy everything from old one to the new one, and now we got a lot of more slack space for future addition. So this kind of exponential resizing. So this guarantees, if you do the math like is the standard exercise in your second course on data structures and algorithms, that the amortized running time of a single add becomes constant time, because every linear time expansion is necessarily preceded by a linear number of constant time adds. So if you take the linear cost and divide it over the preceding linear number of adds, you get a constant per. So then in the long run, the series of operations adds behave as if they were constant time, even though they can be like an occasional linear time expansion in the middle. So the string builder, so it's like a string, but it's mutable, and then so maintains the slack space in the underlying character array, so that adding stuff to the end becomes an amortized constant time operation. So now the two string representations, so create the string builder. So let's use this open square bracket as the starting character, and then so this iterating through. So the current node, so we start from the successor of the head, and then successor, so we end up in the head. So then this loop would immediately terminate. Otherwise, to the result, so append the key and move on to the next node in the chain. And then to make sure that we don't have a silly looking trailing comma in the end, so that if the step didn't take us to the header node, so then we append the comma presentation. So then when we done the full circle around and ended up back to the header node, so then append the closing square bracket, and then now in linear time, so convert the result to set the result in stone to an immutable string. Next, so because we intend to use this as a collection, so let's make it so that this data type allows iteration. So in the Java collection framework, and in general this iterator pattern, so when you have an iterator, so something that you can use to traverse through sequential data without having to worry about the underlying representation. So that you can, for example, iterate through the elements of a linked list and an array and a hash table and a binary search tree and whatever you have. So that's to iterate through the elements one at a time in order without having to know or care about the underlying representation. So we have this abstraction of an iterator. So from any Java collection, you can ask, give me an iterator. So you get an iterator object like a smart finger that is pointing to the logical beginning of the data. And then with that finger, you can traverse through the elements one at a time, and then it tells you when there is no more coming, and that you're done. And all these iterators are separate objects. So into the same data structure, you can have multiple iterators at the same time. They don't need to operate in lockstep like they needed back in some primitive languages back in the day. But each iterator can traverse the data structure back and forth. So also back, because this is a least iterator, so allow two directional moving. So then independently of the other iterators that you may have. So what does the iterator need to know? So the iterator, so conceptually, is pointing between the elements. So that's the way to understand the iterator. That if you imagine that like the idea of a caret. So the way that if you think that how in a text editor, you don't actually have a cursor, but you have a caret. So caret is like that line that is between characters. Cursor is when it's like a highlighting one character. So that's another old-timey terminological distinction. So this iterator behaves like a caret in a text editor, that it's always pointing between elements. Now, of course, so we cannot point, if you have two nodes in the memory, there is like a node between to point at the, so that our current pointer, so this is like where the iterator object is pointing, so it's pointing to the predecessor. So if there is like a two nodes, so it's pointing to the predecessor, but we write the logic that it's as if it's pointing between the two nodes. So current starts at the header node, and then so the Java principle for iterators is that if you use an iterator to modify the data structure by adding or removing the elements, so then this is only legal if your list operation has previously returned an element, and then to add and to remove, they operate relative to that element. So the iterator has to remember what was the last node from which we returned the key. Okay, and I now realize maybe the DL list iterator, I think it needs to be DL list iterator E. Does it need to be? I'm not, okay, so probably. I don't see why it would hurt, but yes, so I never write perfect code. For the past 20 years that I've been teaching at the Chang School, every semester I think that it's always gonna be the last correction that I make to my material, and hopefully so before I retire, so then my examples will be perfect. But I have given up that hope a long time ago. Anyway, so because we're setting the field values into initializer, so notice the constructor doesn't need to do anything. So now the iterator methods, so now this is a list iterator, so allows the traversal in both directions. So we can ask, so is there a next element? So is the iterator cursor conceptually between two elements so that there is a next element? So there is, if from the predecessor that we are pointing at, so then its next element is not the header, because so in a cyclic list, so when the predecessor is the last element, there's nothing after, so then its next element is the header. So this is how we test whether there is a next element. Then the operator next. So start by testing that there actually is a next element. So if there isn't, so then we're gonna be throwing an exception to indicate this. And then we say that we assign, so what is current pointer to point to the successor that becomes the new logical predecessor. But so then we also make that one to be the last return. and then we return the key from that successor. So initially, when our current is pointing to the header node and we access the next element, so then it steps to the actual first element and then returns the key in there that then becomes the last returned. The previous the logic is symmetric, so there is a previous element if we haven't if we're not at the header node. Okay, I now realize what is the intended semantics when we've gone all the way around. Well, like so if we gone past the end of the list, is there a previous element? So I now realize that maybe this logic needs to distinguish between the situation we haven't even started yet, or we gone one way around. So that this doesn't actually distinguish between those two possibilities. So maybe we'll see what we're gonna be doing here. So then the logic for the getting the previous, so there has to be a previous element. And so remember, because the current is always pointing to the one that is logically previous, so then we get the result from the current node, and then it becomes the last node. And now I'm wondering if I'm off by one here. I guess I could have thought about it before I started making the video, but let's see what happens. That's why we write the proper tests. Now iterators, so theoretically they provide the concept of the next index and the previous index, but now because so keeping track of the indices, especially if we are dynamically adding and removing nodes, so would become a linear time operation. So I decided not to support it at all. So then I'm violating the Lisco substitution principle here, but well, I'm not actually. Well, this is an list iterator, so theoretically I should be following the Lisco principle, but do as I say, not as I do. So then I just define both of these operators that they throw new unsupported operation exception. Now the remove operator. So this is about the last return. So if there isn't the last returned element, so then the remove is not allowed. So then we throw an illegal state exception, and then otherwise we unlink the last returned. So now what happens if there are other iterators pointing to that one? Well, because the unlink, the node still remembers its earlier predecessor and successor. So so at least the traversal can continue, but so removing twice. Well, that's why the remove is a list operation, not the node operation. And after removing, last return becomes null, so we can do another traversal operation to either direction, so that the last return becomes non-null, and then the remove becomes possible again. And then set, so what this replaces the key in the last returned node, and then the add. Notice that when overriding, so the add method always takes an arbitrary object as a parameter, which seems kind of strange, but I guess that's what it does. So then we just insert the successor, and now here we do the downcast, and then if the object actually isn't the correct type, so then the downcast is gonna be throwing a class cast. If the class of the specified element prevents it from being added to the list. Very strange that the add method accepts an arbitrary object. It seems kind of weird, but maybe they have reasons. And then that's the end of the iterator. So we're defining this iterator as a nested class. So we don't define it as a static nested class so that it has the access to the surrounding class and its data fields because we do need the head field. So this cannot be class, but the DL is iterator every outer class object from which it was created. So the static nested class, the objects of the static nested class, they can exist independently of the objects of the surrounding class. Therefore, they cannot directly access the members of the outer class object. But this kind of inner class, the object can only exist in the context of some outer class object, and then the outer class object, we can access its fields as if they were our own. So that's the advantage of the inner class. And because the call is coming from inside the house, the murderer is already inside the house. So this because we are inside the outer class, so then we can also see all the private parts of the outer class. Okay, so that was the iterator. Looks like I need to think about it a bit more. But let's take a look at some of the list operations. So now we could, for example, issue a challenge that like take some problem from lead code or similar that is dealing with the linked list, and then implement the problem like for a singly linked list with the head pointer, and then implement the same thing with this kind of a cyclic doubly linked header node list. So I'm betting that it is gonna become a lot simpler. So I can think of like a single situation where this would become more complicated than the typical singly linked linear head pointer list. So first rotate left, so the number of steps. Now this could be done more efficiently. Of course, we could slice an entire sublist and then just link it in two assignments. But just to keep this simple, so just to showcase, so rotate left, so first element becomes the last and all the others take one step to the left. So we take the successor of the head and then make it to be the new predecessor of the head. If we are unlinking the header node, what happens if we rotate an empty list? So it doesn't matter because unlinking the header node just makes it its own. So it doesn't change anything in the next and the break pointers. So of course, we could add as a test that if the list is empty, then do nothing, but just to keep it simple. Rotate right is perfectly symmetric, but we unlink the last node, the predecessor of the header, and make that to be the new successor of the head. Now another advantage, so we see in the contains method, so of using the null object or the header node. So the header node, because it's a node, so it has the key, the payload field, but it's just not used for anything, but it is there. So now we can do variation of a sentinel search. So this is another way. I think I'll show this in the next video or maybe the third one. Yeah, I think that's gonna be the third video that I'm gonna make in this series. So how to optimize various simple array algorithms. But so this idea that so suppose it's like again your normal data structures algorithm course, and you have that lab exercise. So write the method to determine whether the linked list contains a given element. So start traversing through the list, and then inside the loop you have two tests. So first, are you still inside the list? So is your car pointer not null? And if that's the case, so is the key in the current node, is it the one that you're looking for? But with this kind of a sentinel idea, so because the payload field of the header node is unused, so then we can set the key for the purposes of this search to be that the thing that we are looking for. So now when we start from the header node, so actually we start that the current node is going to be the successor. No, so current node, so start from the header node, and now we're doing a while loop. Now, why is this? So now we get to do a do-while loop. Now, do-while loops are like 1% of all the loops in practice, but at least, so do-while loop. So if you're in a situation that the loop has to run at least one round and the condition doesn't make sense until you execute the body once. So those two things, when they come together, you need to be using a do-while loop. So start from the head, so but immediately so move to the successor. And now, so all we don't need to test are we still inside the list. So we only get one comparison per round, not two. So because we placed the sentinel, this key to the header node. So now we're guaranteed when we go around the list that if we don't find the key any sooner, so we're guaranteed to find it in the header node. So we're not going to be running around the cycle forever, because we're going to be finding the key in the header node if we're not going to be finding it any earlier. And then, so was this a genuine occurrence? So they compare, so that it was a genuine occurrence if current node is not the header node. So this kind of sentinel eliminates one comparison from the loop of the search. Now, the downside is that this will fail miserably in the presence of multi-threaded programming. If we have two threads are sharing the same singly linked list and both are searching for a different element, so one of them is gonna win the data race that sets the sentinel value, and then the other one, if it doesn't find the key, is gonna be running around forever. And then so concurrency and multi-threading is just weird when you have a data race. Anything can happen, all bets are off. Next step, so the generalization of the removal. So we can be given an arbitrary test. So does the key satisfy a particular condition? So predicate is in Java 8 function object encapsulating the concept of a predicate. So predicate means a Boolean valued function, so something that returns a truth value, tests whether the parameters have a certain property or they do not have, yes or no, true or false. So especially this removal. So now, because we don't need to handle removing the first element and removing the last element as a special case, so we just start searching from the successor of the header node, and as long as we haven't gone around the full circle so that the current node is not the header node, so then if the predicate, so predicate object as a method test that is gonna do the test that the predicate object is refined. So if the key in the current node satisfies the test, so then we unlink the current node. But again, so because we didn't make the next and the prev pointers of the current node to be null, so even after unlinking, so we can just unconditionally step back to the next node. So no special cases, no edge cases here. So removing the first node, last node, whichever node is handled with the exact same unlink operation. So we know that the current is not the header object, so we are never unlinking the header. And then let's finish this video because this is going longer than I thought. I'll make the other videos hopefully to be shorter, but so let's look at the more complicated method. Let's make this actually smaller. Let's look at the merge routine of the merge sort. That's gonna be somewhere in your first algorithm, and wherever different people put the sorting algorithms in different places of the course. So this merge, so this is typically given for two arrays, but so now let's do it for the linked list, and now in the spirit that we are linking the existing nodes. We're not creating or removing any nodes because that's just inefficient. So this creates a new list and then links the existing nodes to the new list. Both original parameter lists become empty after this operation. We of course could have done the merge so that of the two lists, the one absorbs all the nodes of the second, but maybe simpler this way. So now the concept of sorted merging. So now we have an extra type bound for the element type. So the sorting based on the elements makes sense only if the element type is something that has an order comparison defined. So we can merge two lists if the element types are such that that we can tell from two elements which one's bigger and which one's smaller. If you're sorting like a list of integers or a list of strings, so those are comparable with themselves, so it's all fine. So this one is a static utility method, the merge. So taking the two doubly linked lists as parameters, creates and returns a new doubly linked list containing the nodes of the sorted first and the second list in sorted order, making the first and the second list to be empty in the process. So we can start by creating the result list, creating it as empty, and then just repeatedly, so compare the first, so as long as both lists are non-empty, so that the header of the first list is not the header, the first node of the first list, so it is not its header node, and then the same for the second list. So then compare the keys of the first nodes of both lists. I feel like this could be done in a far prettier way. This is always accessing the keys multiple times. So now the first thing that we could do just to make the code less clean is would be to cache the result of these two expressions in a local variable. So then when the same expression is there, so we don't need to call that method again. So to the result list, add a new last element. So to the result, so link a new predecessor to the header node. So depending on how these two keys compare. So if the key of the first list, the first node is less than equal to the key of the first node of the second list, so then we remove the first node in the first list. Notice that this returns the node, so then we link that node to be the predecessor of the result list header, and otherwise so remove the node from the second list. So this will keep going until one of the lists runs out of nodes. It could be, for example, that all the keys in the first list are smaller than any key in the second, so then the first list runs out of nodes before we take anything out of the second list, or other way around, or any combination thereof. So then in the end, so as long as the first node still has, as long as the first list still has nodes remaining, so link them to the result list. Now, if we had a direct access, well, I guess we do have a direct access. Yeah, so this instead of a loop, so this could actually be done with a single splicing operation, but just to keep this simple. But my examples will never be perfect. And if you're not deeply ashamed of the code that you wrote 5 years ago, I'm now deeply ashamed of the code that I wrote 2 days ago, but that just shows how quickly everything moves. So this is well, this whole thing is still linear, but the whole point of using a linked list instead of the array is that in a linked list you could theoretically splice like an arbitrary long chain, and then in a constant time splice it in to like some other place instead of a linear time. But so here we're just doing a linear time loop, and then the same for the second. And then so once this is done, so return the result list. So this now illustration So hopefully that the advantages, like repeat that last principle. Let's look at the slide in here. That if you have a doubly linked list, you made that decision that every node has the next pointer and prev pointer. So once you made that decision, first make that list to be cyclic. Don't even think about it, make it cyclic. And then use a header node instead of a head pointer. So once you commit yourself that you're doing a doubly linked list, so you might as well commit to these two. Can never harm you, and that then makes a whole bunch of things a lot easier and more efficient time-wise, because there is no null pointers, there is no special cases. Your code is nice and symmetric. Now, whole bunch of things in here. So as I now realize, could be done even better, but that's how it works in life. So let that be the end of this lesson. This video is already long enough. So then the next video I'm gonna do about not being a Schlemiel, how not to be accidentally quadratic, how to avoid it. And then the third video is gonna be take some familiar array algorithms and then see how they can be made faster. So hopefully you'll find this enjoyable, my YouTube viewers and subscribers. If you like this video, please click to subscribe and bling effect, like I know how to make that. Okay, so I guess that's enough for today. So I don't even have any dad jokes to end. So let's end this video so that I can post it.